Variable speed injection mixing is an easy way to control the water temperature for any radiant system, while at the same time providing outdoor reset. But how, when, and where should you install it? And what are you hoping to accomplish? Welcome to Variable Speed Injection Mixing, an 8-part online training program presented by Taco. My name's John Barba, and in this program we'll show you what variable speed injection mixing is, what it does, how to install it, and what products are available to make it easy. Let's get started. So here's the challenge you're facing. You're looking at one of those jobs. You have some high temperature radiation to deal with, such as fin tube baseboard. In addition, there's some high temperature radiant floor heating in between the floor joists with aluminum plates for some carpeted areas, as well as some mid-temperature radiant also between the joists with aluminum plates for areas with hardwood or tiled floors. Now, to make it even more interesting, there's some low temperature radiant as well down in the basement slab. Now, for this job, we're going to choose to use a cast iron boiler, although the same mixing problems would exist if you were using a modulating condensing boiler, but in this case we'll use a cast iron boiler with an indirect hot water tank for your domestic. The question is, how are we going to make this big thing work? So let's think about what we're trying to do here. We're going to need 4 separate water temperatures, 1 high temperature for the fin tube baseboard, and 3 mixed temperatures, 1 for the high temperature radiant, 1 for the mid temperature radiant, and 1 for the low temperature radiant in the slab. And we'd also like some sort of domestic hot water priority control. So how are we going to accomplish all this? Well, no matter what kind of boiler we're going to use, some sort of mixing device will be needed for the radiant systems. Since there are 3 separate and distinct control areas, we'll need 3 separate mixing strategies. Now, we could use 3 separate 3-way tempering valves. These valves are relatively simple and are non-electric and therefore require no additional wiring. They provide a fixed radiant supply water temperature all winter long, but as we will see, they also have a very high pressure drop, which could lead to using larger and more costly circulators. Now, 3 tempering valves certainly would work here, but there may be other options that could be more effective, more economic, and more energy efficient. Now, before we examine the alternatives, let's again review what we need. Since the boiler itself will deliver the hot water for the baseboard areas, we won't need any mixing device for that. We will, however, need some sort of control for the 3 separate radiant water temperatures. In addition, we'll also need zone control for 4 separate water temperatures, including the baseboard. Smart boiler control would also make the system work a little bit better, more efficiently, and ultimately, we'd like to make all of this stuff make sense, be simple, and play nicely together in the same sandbox. As you know from experience, there's nothing worse than trying to shoehorn a bunch of different control strategies together with a bunch of different color boxes on the wall and hope that it does what you want it to do. Primary-secondary boiler piping is the best way to make this job work smoothly and easily. In a primary-secondary system, a properly sized primary loop is piped from the supply hole on the boiler to the return hole on the boiler. Also on this primary loop should be the air separator, expansion tank, and cold water fill. Right after the point where the expansion tank connects to the system should be a properly sized primary circulator. This circulator has one simple job. It comes on whenever there's a call for heat and keeps hot boiler water flowing through the primary until that call for heat is satisfied. The primary loop should be sized to carry the entire BTU load of the building at a selected delta T. For most cast iron boilers, we'll use a primary delta T of about 20 or 30 degrees, meaning the water will leave the boiler at 180 and come back at 160. The secondary loop, as shown here, will deliver hot water to the radiation. In this drawing, we show a secondary loop supplying hot water to a baseboard heat. The pipe and the circulator on the secondary are sized for the secondary load only, along with its associated flow rate and head loss. Now, one of the benefits of primary-secondary piping is that circulator sizing is a lot easier than with other piping arrangements, and in most cases, the selected circulators will be smaller and less costly, but still get the job done. The key to making primary-secondary piping work is the spacing of the 2 T's connecting the primary to the secondary. The T spacing here should be no more than 6 inches or 4 pipe diameters. The theory behind primary-secondary piping is that flow through the primary will not cause, create, or otherwise influence flow through the secondary, provided that the pressure drop in the common piping, that's the piping between those 2 T's, is minimal. So keep that common pipe full This primary-secondary piping arrangement is perfect for jobs such as the one we're looking at today, which is a multi-temperature, multi-load application. Each secondary will be separate from the others. In theory, they will be hydraulically isolated from one another, meaning that flow through any one of the secondary loads will have no effect on any of the other secondary loads. The system we're working on today has a piping component for baseboard. So the rule for primary-secondary is to take the highest temperature secondary off of the primary first, then the next highest, and then the next highest, and so on. Since baseboard doesn't require any mixing, we can pipe directly off of the primary as shown here. After the baseboard, we'll pipe up 3 different mixed temperatures, starting with the highest. There are lots of options available for mixing the water temperature for your radiant system. First, there's the 3-way tempering valve. It's a simple thermostatic non-electric valve. The tempering valve is the lowest cost mixing option available, but it also has the least functionality, providing only a fixed radiant supply water temperature all winter long. The tempering valve has no way of interacting with the boiler either, meaning that the boiler is going to need to fire whenever there's a call for heat, even if there's enough heat left in the boiler from the last time it fired. This can lead to short cycling even in the dead of winter. The tempering valve also has no built-in mechanism for protecting the boiler from low return water temperatures and possible flue gas condensation. Then you have the motorized 3-way valve option from Taco called the I-valve. The I-valve is available in both a set point option and a reset option. The set point version of the I-valve is a motorized tempering valve really. It maintains a specific radiant supply water temperature just like the thermostatic non-electric version does. The I-valve however does have a built-in boiler protection function while the 3-way tempering valve has none. The reset I-valve is a huge step up from the set point I-valve, however, in that it offers a fully functional outdoor reset control on board, right in that green operating head that you're looking at. The reset I-valve will change the radiant supply water temperature based on how cold it is outside. All 3 valves, however, have pressure drop issues. To fully understand pressure drop, we need to become familiar with the concept known as CV. CV is a way of expressing the pressure drop across a piping component. The CV rating of a valve tells us the flow rate across that valve that is needed to impart 1 psi of pressure drop on the fluid. And 1 psi of pressure drop, we know, equals 2.31 feet of head loss. The 1-inch 3-way tempering valve has a CV rating of 3.8. That means a flow rate of 3.8 gallons per minute across that valve will add 1 psi of pressure drop or 2.31 feet of head loss to the system, and that will have to be taken into account when sizing the circulator. The 1-inch motorized I-valve, on the other hand, has a CV rating of only 3. That means it only takes 3 gallons per minute of flow across the valve to impart 1 psi of pressure drop or 2.31 feet of head to the system. This again will impact your circulator sizing. Based on this information, it appears as though the 3-way tempering valve or the 3-way I-valve may be best suited for smaller jobs, say 3 to 4 gallons per minute or so. If that's the case, how do we handle larger applications? Well, the solution seems to be variable speed injection mixing. It's perfect for larger multi-temp, multi-load systems in that injection mixing will allow you to provide several different supply water temperatures, all while staying within a simple primary-secondary piping arrangement. And because of the way it works, injection mixing requires very small pipe and very small pumps. With injection mixing, we can move a lot of heat with small pipe and small pumps by taking advantage of the power of delta T, or temperature difference. We know that delta T determines heat transfer. The larger the delta T, or temperature difference between 2 objects, the greater the rate of heat flow from the warmer one to the cooler one. The same thing happens with water. A wide delta T can increase heat transfer, as we'll see in subsequent episodes of this program. Injection mixing adapts easily to outdoor reset too, which can help create a more effective, more comfortable, and more economic heating system. And best of all, there are a lot of ways to accomplish injection mixing, and we'll look at those in our next installment. Well, that's all for part 1 of variable speed injection mixing. Join us for part 2 when we'll delve more deeply into injection mixing and show how it can solve the pressure drop problems associated with tempering valves and with mixing valves. Thanks for joining us.